we're into chapter 4 now. And in chapter 4, we're going to be studying how forces cause acceleration and friction. And we're going to study mass and weight. And then we will be, in part 2, we'll be looking at Newton's second law. Okay. So, forces cause acceleration is the main idea of Newton's second law. And we've already talked about it a little bit. We've said that if the net force is 0, then the object is in equilibrium. And so those balanced forces, in that case, you could have static equilibrium where the object stays still, or dynamic equilibrium where it moves at a constant speed. But in either case, you've got a balance of forces or no forces on the object. Well, what happens in the third case, where you could have a non-balanced set of forces, so that there is a net force that is non-zero? So a non-zero net force. And so that's what this chapter is about. But first, we're going to learn a little bit more about forces. But also there is the idea that, yeah, acceleration is what results if you've got an unbalanced force. And the acceleration that you get, that depends on the force. So greater forces will cause greater accelerations. But it also depends on the mass. All right, so let's go look at some more forces. We're going to look at the force of friction first. So the force of friction, it's a very common force, of course. And so friction is what occurs between two surfaces, or it can occur between a surface and air or fluids, so like airplanes or boats. And for surface friction between solids, it depends on the kinds of materials and how much they're pressed together. So, you experience this if you rub your hands, okay? If you press harder, you feel the heat building up, right? So lightly pressed together, there's not as much friction. More pressure, more friction. And also depends on the kinds of materials. So if you are rubbing your hand over your desktop, maybe it's nice and smooth, or you're rubbing your hand over, a rough piece of wood, that would be a different amount of friction. And so we have to think about trains. Trains have metal wheels on metal tracks. So there is a lot of research into the values that you get with different surfaces. So cars have rubber on a road that could be concrete or it could be asphalt. So there are lots of different surfaces that will give lots of different results for the value of the friction. Now, the friction is due to the surface bumpiness, but it's more than that. It actually goes down to the atomic level. So there's surface bumps. So if you've got sandpaper, 400 sandpaper is nice and smooth. 120 grit is rough. 60 is even rougher, right? So anyway, so sandpaper is graded by the coarseness of it. But there's also the stickiness of the atoms. Remember when we talked about the normal force, I talked about how electrons repel each other, and that's what keeps an object repelling, okay? So it's above a surface, and that provides the normal force because the electrons repel each other. But remember, there's more than electrons in an atom. There are protons. And so the protons in one material can be attracted to the electrons in the other material, and vice versa. The protons here could be attracted to the electrons here. And so what you actually have are atoms trying to stick together and interact between surfaces. So there's the roughness of the surface, and there is the atomic interactions. Okay, now this matters for you when you are driving a car. Currently it's summer when I'm making this video, so we've got fairly dry roads. So you've got pretty good friction there. But when roads get wet or icy, that reduces the amount of friction. And therefore your tires are not able to give you as much frictional forces, which is what helps you in guiding the car and stopping the car and changes your stopping distance. So actually it does make a difference how much friction there is. And that's why your tire should usually not be bald, is because the rougher the tire here, that's going to give you a better grip. Okay, so anyway, so yeah, so friction definitely matters. Okay, now friction is called contact friction when two surfaces can slide over each other. And the friction is always directed opposite to the motion. Okay, so here we've got somebody is trying to, this block here is being pushed across a surface perhaps. And so as it moves, perhaps it's just sliding along, the frictional force is the opposite direction to the velocity. So the block is experiencing a frictional force that is the opposite direction to the velocity. So anyway, so yes, so it's always opposite the motion. Now, that is called sliding friction too. Or if you've had other physics, you know it's called kinetic friction. Kinetic for motion. The objects are moving. But there's also static friction. Static friction is for things that are slow. Okay, I'm saying that, so things that are not moving. And static friction is greater than sliding friction, strangely enough. And this can occur when you just start to push on a block. So there's no velocity. But as you try to push a block forward, okay, maybe you can push on your book right now, just very gently. And you push on it, and it doesn't move yet. So you're just pushing a little bit, so it doesn't yet move. Well, why doesn't it move? Well, it doesn't move because there is a static frictional force which is holding it in place. So as you push, then this static frictional force occurs. It's zero if you're not pushing, it's just sitting still. But if you start to push, the force starts to grow. And the harder you push, the greater it is. And what's going on is the molecules are locked to each other because they've been sitting there nice and still and interacting. So as you start to push, then suddenly what happens is it reaches a maximum value, and then the object starts to slide. Okay, so you're pushing with the force. Now you've got a velocity, but not till after you've reached that maximum static friction value. And then once you started sliding, it's much easier. So you've experienced this, right? So you can push on something, and then suddenly it starts to go. You got it moving, and then it moves along easily, or more easily. You don't have to push as hard anymore. So anyway, that's because you had to break the static friction lockdown so that you could then have sliding or kinetic friction. And so this frictional force gets larger and larger and larger as you are applying a force, and that's a kinetic, let's say the static friction force, and it reaches a maximum value and then down to the kinetic friction. And that's when you're sliding along, it's less. Now, strangely enough, a tire because this point makes contact with the road and is still for a tiny, tiny fraction of a second, it actually has static friction. And so this is important because that's actually a greater amount of friction. As long as your wheel is moving, so that or still, then so if it's rolling or still, then that point is static friction. And so that's why it's dangerous when you get in water or ice, because or if you jam on your brakes so they lock, what happens is that instead of static friction, the wheel starts to slide along. Well, then it's kinetic friction or sliding friction, and that's less. So you get less control of your car if you lock your brakes. And that's why cars have anti-lock braking, so that your tire never actually is absolutely still until your car is at rest. So the tire goes in little pumps and little, it just keeps going a little bit. So if you've ever felt as you push down on the brakes really hard and you feel it kind of thumping underneath, that's because the anti-lock braking system is allowing your tire to move a little bit because they don't want it to lock, because then you'll just slide across the road. Okay. So anyway, so yes, so that's what anti-lock braking is for. And it used to be when I was young, before anti-lock braking, you had to do it yourself. So you were taught to pump the brake, but yourself with your foot to try to keep it so that it was rolling a little bit, so that you had better friction. Okay, so that's what the anti-lock braking or APS braking system does. Okay, now, as we said, friction is always in the opposite direction. And so that also is for air resistance or air friction. And so as you drop an object and it's falling downward, the frictional force, of course, will be in the opposite direction, upward. Okay, so friction up, right, opposing the downwards direction, which is the direction of the velocity in this case. Okay, now, some interesting things about air friction is that it is proportional to surface area, which, by the way, regular contact friction isn't just surface area. Remember, we talked about the forces that you have to push it together. That increases it. But air friction is proportional to the surface area. So when a person falls out of a plane and they want to slow down, of course, they increase their air friction by increasing their surface area, right? And so pulling the parachute makes a larger surface area. Or people, when they jump out of a plane, they can spread their arms out. So, you know, there are those suits that are allow you to fly like a flying squirrel, because they increase your surface area. They give you more friction to control your flight. And so it depends on your surface area. But another weird thing is it depends on your speed. So surface area and speed. So as this person falls out of the plane, when he first falls out, his speed is almost zero. So his air friction is almost zero. And then as he falls downward, increasing his velocity, well, his air friction also increases. Anyway, but in the opposite direction, of course. But yeah, they increase together. So velocity increases, the air friction goes from zero when he's high up down, and as he gets larger and larger, it could be 200 newtons, 300 newtons, 400 newtons, 500 newtons. We'll talk about that more at the end of the chapter. Okay, so anyway, so yes, so the air friction increases as the velocity increases. Okay, another thing we're going to discuss is inertia. Now, inertia is that natural tendency of an object to remain in a state of rest or in uniform motion in a straight line, and we talked about that with Galileo. Remember, uniform motion means constant speed. So think about a bowling ball, right? A bowling ball, once you start it rolling, it wants to remain rolling. It's going to keep going. It has a large mass. And so it's easy to stop a ping pong ball, but it's harder to stop a bowling ball. And that's because a bowling ball has more inertia. And Newton took Galileo's ideas and he related mass to inertia. So when you have greater mass, then the greater inertia. So the bowling ball has more inertia, more resistance to changing its motion, so you have to use more force if you want to change it, than the ping pong ball, because it has greater mass than the ping pong ball. Okay, so mass relates to inertia. So basically when you're saying something is 15 kilograms of mass, you're also saying it has 15 kilograms of inertia. And remember, mass is different than weight. Oops, skipped one. So here's a big guy and a little kid on a swing. Well, the big guy, grandpa, has more inertia. And so when you push on him, it's going to take more force to get him started and also more force to stop him. You might step into the little kid and grab onto it and stop them, but you don't want to do that to someone who's bigger, right? Because there's a lot of inertia. And so, yeah, big masses have more inertia. And so if the kid is 50 kilograms and he's 500, oops, sorry, I wanted to, sorry, he's 50, okay, and she's 5 kilograms, which is, yeah, that would work. So he would be like 500 newtons of force. Okay. So anyway, so remember that people are around 50, 60, 70 kilograms. Okay. So anyway, so let's say he has 10 times as much mass as she does, then he's going to have 10 times as much inertia. Okay. So 500 newtons or 50 kilograms. Okay, so let's make that a little different. Okay, so let's say that she is 10 kilograms and he is 100 kilograms. Okay, so anyway, so the idea is that 10 times more mass, 10 times more inertia. And so 10 times greater resistance to changing its motion. Okay, now mass, again, we talked about this in the metric system review. Mass is the quantity of matter in an object, so how many atoms it has, basically. But it is also a measure of the inertia of the object. And we do measure it in kilograms, right? So this is 1 kilogram. And you can measure it in kilograms, or we talked about how slugs are actually the unit in the British system. It's just we don't use it. Anyway, so here's the standard kilogram. So we talked about that before. Okay, now weight is the force of gravity on an object. So mass is different than weight. Inertia, I can think about as what I have to do to change the motion of the object. So when I wave it back and forth, I'm looking at its inertia. But for weight, I have to weigh it, right? It's the force of gravity. So I have to think about, oh, how hard is the earth pulling on this kilogram weight, right? So that's the force of gravity. And weight is actually a force. And then measured in newtons. And how much is a newton? Well, this red apple has a mass, or a weight anyway, of 1 newton. And so that would be about 1/10 of a kilogram. So it's about 1/10 the mass of a kilogram mass. And so it's not a very big, it's like Newton is associated with apples because he had the story of the apple under the tree. We'll talk about that more in gravity, that fell and helped him with his ideas of gravity. So anyway, so Newton's name is associated with apples, and it's about the weight of a small apple is about 1 Newton. Now, weight changes if the acceleration of gravity changes. So you go to another planet, or you go somewhere else on the Earth that's a different place. The gravitational field is not the same everywhere on the planet Earth, and the acceleration of gravity is not the same everywhere on the planet Earth. And you can calculate weight by multiplying the mass times the acceleration of gravity. And mass is the same everywhere on Earth, but weight isn't, because that G could change. Okay, are you on the planet Earth? Are you on Denver? Are you in South Carolina? That would be actually a slightly different weight, but mass would still be the same. And remember, we're going to use 10 meters per second, or 10 meters per second squared for the acceleration due to gravity around the Earth. So the real value, remember, is 9.8. We're going to use 10 because it's so much easier to do the calculations. And so anyway, so weight can change, but mass is a constant. So let's say I've got a 4 kilogram mass. What would be the weight? Well, I would just take 4 kilograms and multiply by 10 meters per second squared, which is easier to write. And I would just end up with 40 newtons. Okay, so 40 newtons. So whatever the mass is, you can just multiply by 10 to get the force. So 40 newtons. So how much weight is on this 1 kilogram? Well, the mass has to be in kilograms in this calculation to come out right. So I would just have 1 kilogram times 10. So this has a force of 10 newtons. Okay, 10 Newton object. That's how much gravity is pulling on it with. Okay, so weight changes, but mass is constant. Okay, so what is the weight of a 2.45 kilogram banjo on the Earth or on the moon? Notice the mass stays the same, right? But force is going to be different. And so the moon's gravity is only about 1/6 that of Earth. Okay, so you just use the formula. Weight is mass times G. And so we've got our 2.45 kilogram banjo times 10 makes 24.5 newtons, right? Now, if we take it to the moon, then we can take the same mass, but now we're going to divide it by 6, and that's going to end up 4.1 newtons. Okay, so it is 1/6 as much weight on the moon, but the mass is still the same. And by the way, of course, we don't usually play the banjo on the moon because it would cost a lot of money to get a banjo there, and there's no air to carry the sound waves, right? Okay, so Newton's first law of motion we talked about before. And it's basically based on what Galileo said, that objects at rest can stay at rest. Objects in motion will stay in constant speed motion unless they are acted on by an external unbalanced force. And so, yeah, Galileo said things could just remain in motion indefinitely, forever, if no other forces come along to disturb them. So that bowling ball that you sent sliding down the track, right, it could keep going forever, except at the end there are pins and other things to keep it from going forever, right? So you roll a ball, right, throw a rock, that rock could go forever, except gravity, or whatever it is you hit. So anyway, so yes, so out in space where there are only the forces of gravity or micrometeors or things like that, then spacecraft will keep going and going and going. So as I've said, the Pioneer 10 and Pioneer 11 spacecraft, the Voyager 1 and Voyager 2 spacecraft are still out there moving after 50 years. They're still going, and they're still sending back information too. Okay, so yeah, they don't need any engine on them to just keep going. All right, so that's the end of this talk. All right, let me stop it, and we'll restart for the second part.